you will always be working with moles and molarity, although you probably not necessarily realize it at that point. So the first thing is that we need to understand what mole actually means. And mole is nothing else but just simply a number. I heard people in their third year bioscience degree saying, I never understood what mole is. And you think, oh, shoot, where did I go wrong? They still thought it's a little mammal with a furry coat and digging in the soil. Mole is nothing else but just simply a number. It's a little bit like a dozen. You know what a dozen is, yeah? It's 12. You know what a baker's dozen is? 13, exactly. You know what a gross is? No? It's 12 times 12. You know what a mole is? A mole is 6.022 times 10 to the 23 of something. So, and it's basically this guy here, Avogadro, came up or determined this number. I'm not entirely sure if I want to take his number. He looks a little bit creepy. But hey-ho. 6.022 times 10 to the power of 23, that is actually a mole. And very often we don't deal with whole moles, we deal with lower units of that, millimole or micromole or nanomole, picomole, things like that. Yeah? So please, I know that people develop a sort of almost an irrational fear of things. Moles don't bite. Well, at least not these chemistry moles. And if you just think of it as a mole is a number, then I think for me it's no longer scary, really. Mole is a number, nothing else. It has been actually in the year 2011 and has been redefined. And basically the mole is, one mole is defined as the amount of atoms that you find in 12.0 gram of carbon. So you can imagine there were a few PhD students sitting there and counting atoms. 1, 2, 3, 585, 586, and so on. No, it's not how it works. But there are actually experimental ways to determine this Avogadro number. So this is also called the Avogadro number. Avogadro number. And this basically allows you to make an educated guess of how many atoms or molecules or entities are flying around somewhere in a solution or in a solid or something like that. Does that make sense so far? Now, very often in biosciences we deal with solutions, and if you have basically 1 mole of a substance in 1 liter total, this is called a 1 molar solution. 1 molar solution. And because we are all extremely lazy people, and time, bless you, and time is valuable. Well, you sound healthy, huh? Fresh as flu. What? Do you know what a good remedy is against cough? A strong laxative. It doesn't stop you from coughing, but you think twice if you want to. Thank you, yes. So for a 1 molar solution, we just simply write 1 capital M. This indicates it's a 1 molar solution. It indicates it is 1 mole per liter. Right? So you know that you have 6.022 times 10 to the 23 particles in a total of 1 liter. That's this M. Please don't write it with lowercase m, because that means meter. That doesn't make sense. Yeah? Are you happy with that? Right. Very often what you need when you are dealing with moles, you need a molecular weight. Molecular weight. And this molecular weight just simply tells you how much 1 mole actually weighs. So this indicates how much 1 mole weighs. And how do you find this molecular weight of a certain substance? Well, this is where, for example, the periodic system comes into place. You have probably seen that very often on the periodic system, you have something like, let's say, 816 oxygen. Right? You have seen something like that, yeah? Now this means, actually, this lower number, this means the position in the periodic system and how many protons this guy has, this oxygen has. So this is 8 protons. And this number here, the 16, means how many particles in the nucleus it actually has in total. So we have 8 protons. And 8 neutrons. That's chemistry stuff, yeah? But the great thing is that this number here, the 16, also tells you how much 1 mole weighs in gram. So this 16 tells you that 1 mole of O is equivalent of 16 gram. Does that make sense? Yeah? So, and you can, if you have a more complex substance, you can add up these molecular weights, if you like. So you have 1680 and 2, no, sorry, we don't make 2. We make 1, 1H. Yeah? So what is the molecular weight of water? So 18, so we have 2 times 1 plus 18, plus 16, sorry, gives us 18 gram per mole. Yeah? It's fairly straightforward. You can do that basically with any kind of substance. So, for example, oh yeah, let's do 12,6 carbon. And we want the molecular weight of glucose. Glucose is C6H12O6. What's the molecular weight? $168? Anyone else? Is it 168? $16, $12, $30. I make it 180? Yeah? 180? Sold, bang, it's 180. So you see, you can very easily determine the molecular weight as long as you have the formula for your substance. Actually, do you know how I did that? Very quickly. This is, I know glucose. What kind of molecule is glucose? A carbohydrate. How would you write carbohydrate? No? CH2. It's a carbohydrate. Yeah? And in this case, 6 times. So what I do, just in my head, is C is 12, plus 2 is 14, plus 16 is 30. 30 times 6 is 180. Carbohydrate. Yeah? So you can very easily determine these, the molecular weight. Sometimes life is a bitch. And then you marry one. I'm not making any comments here. Very often people don't really write explicitly molecular weight. Sometimes they just simply say a compound or substance, and they say it has 45 Dalton. And you think, so this DA stands for Dalton. And you think, what the heck is a Dalton? Not to worry about it. This Dalton is sort of almost short form for a unit. So Dalton is 1 unit. Now that doesn't help us a lot. But 1 unit is defined as having a molecular weight of 1 gram per mole. Chemists can be absolutely awkward. Yeah? So whenever you see 45 Dalton, you know that this substance actually has a molecular weight of 45 gram per mole. With low molecular weight substances, usually people are more reasonable and they don't go for this nonsense Dalton. But when it comes to big molecules like proteins, we will find that it's very common to indicate that this protein is, let's say, 23 kilodalton protein. You hear people saying It's a 23 kilodalton protein. And this basically means that the molecular weight of this protein is actually 23, what is kilo? 1,000. 23,000 gram per mole. Yeah? Or 23 kilograms per mole. So if you take 6.022 times 10 to the 23 molecules of this protein, whack it on a balance, you have 23 kilograms exactly. Yeah? So don't be upset or confused if you come across something like kilodalton. You know what it means now. Make sense so far? Fabulous, fabulous, fabulous. What else? Oh yeah, we've got occasionally. Okay. Now, one of the things that we very often deal with is, let's say we have a solution. We have a solution, let's say this is 10 milliliters. And this solution has what is called a concentration. Now, concentration is basically amount of something in a certain volume. So it could be amount of atoms or molecules in a volume. That's concentration. Don't confuse that with moles. Mole is just simply a number. It's an amount of something. That is a mole here. This one. A concentration is this one. It has the volume component in it as well. So, for example, I could say we have about 250 people in one room. 250 would be the amount. 250 per room, that is the concentration. Yeah? Please be always aware, amount and concentration are two different things. Reminds me of the stupid joke that I read recently. You see a lady, could be a gentleman, with a certain hair color, could be any hair color, standing in a supermarket, staring at a carton of orange juice. Why? It says concentrate, exactly. Ha ha ha! Right. So, let's say a solution is always defined by its volume and by its concentration. So, for example, let's say we have a concentration of 10 millimolar. So this here means 10 millimolar. Or in other words, it contains 10 millimole per 1 liter. Okay, happy with that? That is what this 10 millimolar actually indicates. Very often, we want to know how many moles are actually in this volume here. So, how many moles are in 10 milliliter? I want to know how many moles are there. How would you do that?
Do concentration times volume.
Why?
You just rearrange the equation.
You're absolutely right. Absolutely right. Is there another way? Obviously there is. What did you learn last week? Dimensional analysis. Aha. Yeah? Aha. So, what is the unit that we are looking for? Mole. So, do we have mole anywhere? Aha, we have 10 milli means 10 times to the minus 3. 10 to the minus 3 mole per liter. Yeah? That's this guy here. Now we've got our moles. We need to get rid of the liter. Do we have liter anywhere? We know that 1 milliliter equals how many liters? 10 to the minus 3 liters. Exactly. So we have liters here times 10 to the minus 3 liters per 1 milliliter. Now our liters cancel out. Yeah? We just have these milliliters, the pesky milliliters. Do we have milliliters anywhere? 10 times 10 milliliters. So what we have now is we have 10 times 10, that's 100, times 10 to the minus 3 times 10 to the minus 3 mole. So that's this one, that's this one, and this one. Make sure I haven't forgotten anything. 100 I can write as 1 times 10 to the 2 times 10 to the minus 3 times 10 to the minus 3 mole. Yeah? No? A question? Oh, okay. And that gives me minus 6. 2 minus 6 is 1 times 10 to the minus 4 mole. Yeah? So I know that in my liquid here, I have 1 times 10 to the minus 4 mole. Is that the same that you got with your method?
No, because you're going to have to change. Drop back on change.
Actually, it is. Just say yes.
It is the same.
It is. Just say yes. Yeah? Because what you just suggested is exactly the same thing. What we do is we take the concentration here and we multiply it with the volume. So in order to get moles, if you don't want to do the dimensional analysis, what you just simply do is moles equals concentration, which is sometimes abbreviated with C, which is horrible because C for a physicist means the speed of light. But in this case, it doesn't make sense. C times volume. So concentration times volume. Okay? That gives us the number of moles in a volume. Yeah? Not a miracle. Nothing special. But it gets then interesting. Gets very interesting when we go in the lab and when we work with solutions in the lab. And I tell you what, this is where loads and loads and loads of final year students who didn't pay attention in my lectures, of course not, this is where they get very close to a nervous breakdown. I tell you what, I love it. I love it. It's fantastic. You know, the smell of fear. When you say to a student, okay, you have, what have we got? You have a 1 molar stock solution. This is what's on the shelf. You bought that or somebody made it up. But actually, what you really want is not a 1 molar stock solution. You want actually 200 milliliters of a 0.2 molar working solution. And this is where the tears start to stream. And say, I can't do it. I don't know what to do. Yeah, exactly. There's a high-pitched noise then as well. You understand the problem that we have. We have undiluted vodka. Yeah? And we want it diluted. How do we do this dilution? Okay, let's think about it like that. That is our stock solution. And that is our working solution. In this working solution, we should have 200 milliliter of a 0.2 molar concentration. Can we actually calculate how many moles do we have? How many moles do we have here? Can we calculate that? You can either do it with the concentration times volume, or you can do it with dimensional analysis. Shall we do it with the concentration times volume? It's probably an easier step. So moles equals concentration times volume equals, the concentration is 0.2 mole per liter, and the volume, we need to have the same units. The volume is 0.2 liters. That's my 200 milliliters here. Yeah? Are you happy with that? What do you get? 0.04 mole. Actually, the liters cancel out. Sort of half-hearted dimensional analysis, what I've done. So, we need 0.04 mole in here. Okay? Now, where do these 0.04 moles come from? They come from our stock solution. So we have to take 0.04 mole out of the stock solution. Yeah, right. But how do we know how much is 0.04 moles? What are we looking for? We are looking now not for moles, how much we have in there. We are looking for how many liters or milliliters we need. Yeah? Does it make sense? So how many liters do we need? So let's do dimensional analysis again. Oh, yeah, I know. That's a pain, huh? But if you don't know exactly what to do, then I show you in a minute a much easier way. So, liters. Okay, we know that this is 1 molar solution, so it's 1 mole per liter. So we've got 1 liter here. So 1 liter, was it 1 molar? Yeah, 1 mole. Now the liter is in the right place, but we have to deal with this mole. Do we have mole anywhere else? Times, exactly, that's what we want here, 0.04 mole. And you see the moles cancels out, so we need 0.04 liters. 0.04 liters have exactly the right amount of moles that we want, that we need to put in here. So what we actually did was, we first calculated how many moles do we want in our working solution, and then we calculated how many moles we have to take out from our stock solution. Make sense? Now, for those of you who have done some chemistry, this is quite a famous equation. This equation says C1V1 equals C2V2, because that gives you the mole in the stock. And that gives you the mole in the working solution. And both moles need to be the same. Yeah? So if you're looking then for the volume from the stock solution, what you do is you just simply rearrange this equation and you have V1 equals CV, C2V2, divided by C1. Yeah? Does that look familiar? Yeah? Are you happy with that? Now, I am always slow with learning. And for me, this C1V1 equals C2V2 is already, almost a little bit too much. I'm just the bearer of a very small brain. And when I shake my head, it rattles. So this is almost beyond me, this equation, because I never know what is C1, what is V2, and things like that. So whenever I come across a problem like that, I have almost a sort of a crazy image in my head. A guy comes into a pharmacy and he has a prescription in his hand, bless you. And the prescription, on this prescription, the doctor has written, give this guy, say, 200 milliliter of a 0.2 molar solution. Otherwise, he will die. Yeah? So this is what the doctor says. Doctor says 200 milliliter and 0.2 molar. Doctor says two things. Here's the counter. And the pharmacist says, I'm terribly sorry, we only have a 1 molar solution. That's exactly the problem. And all I need to do is, I say, doctor times doctor divided by the pharmacist. Doctor says two things, the pharmacist says sorry. 0.2 molar times 200 divided by 1 molar gives you your answer. Sorry? Doctor divided by pharmacist. I'm not doing the C1V1 equals C2V2, but if you want to do that, that's absolutely fine. When I have to dilute something, I think of this really hot pharmacist, of this pharmacist, yeah. Doctor gave me the prescription and I, yeah, you can dream. Yeah, and here it is. 0.2 molar times 200 milliliter divided by 1 molar. And I've got 40 milliliters. Simples. Yeah, make sense? Now let's do Steve Jobs, you know, Apple, rip in peace. There's one more thing that I want to mention to you with these solutions. Usually, we have a concentration given in mole per liter. But sometimes people use something slightly different, which can lead to terrible confusion. Instead of mole, they use the unit gram per liter. Or something slightly different, they use the unit gram per 100 milliliter. May they rot in hell. Yeah? Gram per 100 milliliter. Who on earth, in their right mind, would like to use something like that? Terrible. Actually, when you are working in a hospital environment, you will come across that very, very often. Gram per 100 milliliter. So this here is a solid substance. And this here usually is a volume of liquid. Or it's just a volume. And because it would be convenient to have it in a format like that, people don't write it like that, because it would be convenient. And we don't do convenient. We want to make things complicated. The more complicated, the better. Yeah? It's a little bit like, can you get syphilis on a public toilet? The answer is yes, you can, but why so complicated? You know, there are other, much easier ways to get syphilis. And instead of gram per 100 milliliter, people make an assumption. They make an assumption that 100 milliliter is water. Now, can you tell me how much 100 milliliter will weigh? 100 grams, if it is pure water. At, I think, 4 degrees or something like that. You know. So 100 milliliter of water is 100 grams. Now what you can do is you can write this gram per 100 milliliter. You can write this as gram per 100 gram. Yeah? Make sense? And now, because life is so complicated, you cancel out the grams. What can you write 100 as? As percent, exactly. You can write this as percent. So that would be percent. So, going back to the less complicated things, a 5% solution, and it's usually abbreviated 5% weight per volume, solid in a volume. 5% solution means 5 gram in 100 milliliter. bugger all biochemists, eh? Who came up with something like that. But I want you to remember this. A 1% solution, weight per volume, equals 1 gram per 100 milliliter. Make sense? This is basically everything that you need to know about making solutions and converting solutions. What I will do on Thursday is I will give you, we will do a few examples together, how we do these things, yeah? As homework, you will get one question only. And this question I'm really proud of because I got my PhD students into absolute despair about this question. And I said to her, look, you're a PhD student, you need to know these things. And she just, she cursed me. I want to know from you what is the concentration in mole per liter of water. What is the concentration of water? Huh? What's the concentration of water? Go in peace.